Okay, hello. So with this video, I would like to tell you about Bernstein's theorem. And roughly speaking, this states that any minimal graph over the entire plane must be flat. So we'll get into a precise statement of this theorem in a little bit. But I want to contrast this to, so I want to say I want to talk a little bit about the context first. So the setting is that we have some function such that the graph is a minimal surface. So we've seen this means that the function f satisfies the minimal surface equation which we'll abbreviate by saying MSE. And this minimal surface equation we can write two separate ways. So in divergence form, we can write this as the divergence of the vector field gradient f divided by square root 1 plus the length of the gradient squared equals 0. Or we could write this in non-divergence form. If you write this out, you'll find something that looks like 1 plus d2f squared d1 squared f plus 1 plus d1f squared d2 squared f minus 2, that is a 2, d1 f, d2 f, d1 d2 f equals 0. So this is a nonlinear quasi. This is a nonlinear quasi-linear elliptic PDE. And what Bernstein's theorem says is that if f is a global solution to the minimal surface equation, a solution on all of R2, then f must be an affine function. So this is in contrast to the case of harmonic functions. There are many more globally defined harmonic functions on R2. You take the real or imaginary part of any entire harmonic function, so you have huge families of infinite dimensional families of harmonic functions on all of R2. You take the real and imaginary part of any globally defined holomorphic function, you get a bunch of these things. So the proof we're going to present follows up on our discussion of isothermal coordinates, and it's very particular to 2 dimensions. And towards the end, I'll state some of what's known in higher dimensions, but we'll leave those comments for later. So what do I want to do? I want to so for the moment, we're going to let D So the following lemma. So we're going to start with the following lemma. We're going to build up our proof of Bernstein's theorem with this series of lemmas. And the first one is the following. If I let, if D is convex and I have a convex function so I can say that one way to say that this function is convex is to say that the Hessian matrix, the matrix of second partial derivatives of this function E, is a positive definite matrix at each point. And then I'm going to do something a little bit strange. I'm going to define the mapping. U gets sent to the gradient of E evaluated at the point U. Then I have the following inequality. So I'll write this as V minus V tilde dot product with U minus U tilde is greater than 0. And another way to write this is to say the following: the gradient of E evaluated at U minus the gradient of E evaluated at U tilde dot product with U minus U tilde is greater than 0. So let's go ahead and let's prove this. And this is a simple consequence of the fact that the matrix of second partials is positive definite. So I'm going to start by just restricting my function to the line segment joining x and x tilde. And this I can do, this is well defined by convexity. So in fact, the convexity of D is exactly the condition that this line segment lies inside D for any choice of x and x tilde within D. Sorry, this should be U and U tilde. Sorry about that. Right. So what do we see? We see that G prime is gradient E evaluated at TU plus 1 minus TU tilde. If I take one more derivative, I see that G double prime is exactly the Hessian matrix evaluated on the two vectors U minus U tilde. U minus. Oh, sorry, this is that dotted with U minus U tilde. And if I write out what this, is as a symmetric bilinear form, I'll see that it's D squared E DUI DUJ. I have to sum over both I and J. U I minus U tilde I U J minus U tilde J. Okay, but this matrix is positive definite, so this sum must actually be positive. So what do I conclude? I conclude that G prime is increasing with respect to T. And as a consequence, G prime of 1 must be greater than G prime of 0. But if I write out what this is, I see that the gradient of E at U dotted with U minus U tilde must be greater than the gradient of E at U tilde dotted with U minus U tilde. And if I rearrange this, I get the inequality V1, we have the inequality V minus V tilde dotted with U minus U tilde, which is gradient E at U minus gradient E at U tilde dotted with U minus U tilde. It's positive. So that completes the proof. Okay, so this is fine. Next thing we're going to do is we're going to define the Louvy map. So I can write the Levy map as C applied to U is the vector U plus the gradient of this function E. This mapping satisfies the inequality C dotted with minus C tilde dotted with U minus U tilde is strictly greater than the length of U minus U tilde squared. So we'll see in a minute that this means the Levy map, this thing that I've written down, is strictly length increasing and strictly area increasing. It's a strictly increasing map. So how do we prove this? This is actually going to come very quickly from what we just showed. So if I rearrange C minus C tilde from the definition of the Levy map, I get this expression over here. And then when I take the dot product with U minus U tilde, I get the length of U minus U tilde squared plus the dot product of V minus V tilde with U minus U tilde. Which is strictly greater than the length of U minus U tilde squared, because we just showed that this second term is positive. Okay. So there's a very quick corollary we see from this. There's a very quick corollary we see from this, which is this: as in the Levy map above, we see that the length of C minus C tilde is strictly greater than the length of U minus U tilde. And this actually follows immediately from Cauchy-Schwarz. So then the length of U minus U tilde squared is strictly less than the absolute value of C minus C tilde dotted with U minus U tilde is less than or equal to this thing. And then the result follows. Okay. So we see from all of what we've done thus far the following lemma. In the special case that this D in the special case that D is the disk of radius capital R centered at the origin, the Levy map defined above is a diffeomorphism, C1 diffeomorphism onto its image. And this domain omega, which is the image, contains the disk of radius capital R. Let me write this way. It contains the disk of radius capital R centered at C of 0. So you don't know immediately that C of 0 is going to be the origin, but wherever this point is, the domain capital omega contains a disk centered about that point of radius capital R. Okay. So because we know that E is a C2 function, this Levy map is C1. But what else do we know? We also know that the length of C minus C tilde is strictly greater than the length of U minus U tilde. So as a consequence, the Jacobian dc du has length everywhere greater than 1. So from this, we see immediately that, so first of all, we see that C is 1-to-1. And second of all, we see that C is a local diffeomorphism. And as a consequence, we see that C is in fact a diffeomorphism onto its image. Okay, so finally, we want to show that omega contains a disk of radius capital R about C of 0. So there are two cases to consider, really. If this capital omega is all of R2, then the result trivially holds. Otherwise, well, what do I know? I know that R2 minus omega is a closed set. So I can select some C bar such that the distance from C of 0 to C bar is equal to the supremum of the distance from eta in R2 minus omega is equal to the distance from C of 0 to eta over all eta in R2 minus this domain omega. Let's write this a little bit more neatly. Eta bar in the complement such that the distance from eta bar to C of 0 will be equal to the supremum of the distance from eta to C of 0 over all choices of eta in the complement. Of course, what's going to happen is that this C bar must lie in the boundary. So I can choose some sequence CK lying inside my domain D, which remember is the disk of radius R centered at the origin. Such that I can choose CK in omega such that CK tends towards C bar, but then CK is going to be C of some UKs, and UKs have to lie inside the disk of radius R centered at the origin, but the UKs actually have to go to the boundary of this disk. And what does that tell you? That tells you that the length of UK minus 0 goes to R. So what do I know? I know that the length of CK minus C of 0, this has to be greater than the length of UK minus 0, but that goes to R. And as a conclusion, we see that the length of C bar minus c of 0 has to be greater than or equal to r. And we conclude that my domain omega contains a disk of radius capital R centered at c of 0. Right. Okay. So now we're ready to apply all of this machinery associated to the Levy mapping to the minimal surface equation. Okay, so what's the setting? I'm going to let F be a solution to the minimal surface equation. On the disk of radius r centered at the origin. So just remember what the minimal surface equation is. It says that the divergence of gradient f over square root of 1 plus gradient f squared equals 0. Okay, so in this case, let's go ahead and build this up. So what do we know? So let's remember some notation from the last time. So some of the notations last time we had P and Q represented the gradient of F, and then R, T, and S represented the second order partials. And we also defined W to be the square root of the determinant of the metric, which we could write as the square root of 1 plus the length of the gradient squared. We could write that as square root of 1 plus P squared plus Q squared. One thing we saw from the minimal surface equation, so we can write the minimal surface equation as the divergence of the vector field P over W, Q over W equals 0. And we see this means there exist functions F and G such that So I can write this as the gradient of f is equal to 1 plus p squared over w pq over w, and the gradient of g is pq over w 1 plus q squared over w. And then you see that, again, the minimal surface equation implies there exists a function e such that the gradient of E is actually equal to capital F and capital G. And if I compute what some of these partial derivatives are, I see that d1 squared of E is df du1, but that was 1 plus p squared over w. That was a given. And what is the determinant of the Hessian matrix of E? That is going to be, so I'm going to get something that looks like df du1 times dg du2 minus df du2 times dg du1. That is exactly 1 plus p squared times 1 plus q squared minus pq squared over w squared. And if I write out what this is, I'm going to have something that looks like 1 plus p squared plus q squared over w squared. Now I have to remember what w squared is. That's 1 plus p squared plus q squared. And w is the square root of 1 plus p squared plus q squared. So this is exactly equal to 1. And the point is that now I see the determinant of this matrix is 1. The entry in the upper right-hand corner is 1. So the fact that the determinant is equal to 1 means the whole matrix is either positive definite or negative definite. This is a 2 by 2 matrix. The fact that this entry is 1 tells you that it has to be positive definite. So I see that E squared E is positive definite. And thus I can apply my Livy map, and I see that then the Livy map with this constructed E maps onto a ball, a disk of radius capital R. So I have this Livy map mapping the disk of radius R onto some domain D, some domain capital omega, and I know that the disk of radius R over C of 0 has to be contained inside this domain D. This is an diffeomorphism. Okay, at this point, we see how to tie in the setting for isothermal coordinates with the following lemma. So I'm going to take some domain. So here, D is some domain contained inside R2. I'm going to take a C1 function, necessary and sufficient conditions such that the surface given by the graph of this function lie in a plane is that there exists a non-singular linear transformation such that the new coordinates after this linear transformation give isothermal coordinates on S. Okay, so one direction is actually very easy. Okay, so I'm going to suppose there exists such a linear transformation. Sorry. Yeah, no, that's fine. Suppose there exists such a linear transformation, and then what do? Well, I'm going to write down, so as in for isothermal coordinates, we're going to let C, let's let Z be U1 plus I U2. And let's write down Vk of Z is going to be d UK dV1 minus I dUK d2. And we're also going to have K. This I can do for K equal 1 and 2. And phi3 of Z is then going to be dF dV1 minus I dF dV2. Okay, but what do I know? I know that because u and the u's and the v's are related by linear transformations. I know that the phi1 and phi2 are constant. But what else do I know? I also know that from last time. That that these coordinates v1, v2 are isothermal. Is equivalent to saying that phi1 plus phi2, phi1 squared plus phi2 squared plus phi3 squared, these all sum to 0. But if these first two guys are constant and the sum is equal to 0, I see that then phi3 must also be a constant. But if phi3 is a constant, that tells you that the gradient of f is constant. And if the gradient of f is constant, that tells you that f is affine. So the converse we can construct very explicitly by just letting if f of u1, u2 is ax au1 plus b u2 plus c, then I can let lambda squared be 1 over 1 plus a squared plus b squared. And I can let v1, let's say u1 is lambda a phi1 plus b v2, and u2 is lambda b v1 minus a v2. And this gives an explicit solution. Okay. So we've seen now the condition to have this graph lying in isothermal coordinates is actually that the condition that the graph lies in the plane is actually something that says that there's a nice expression, there's a nice linear transformation that gives isothermal coordinates. So we can finally use this to prove the following theorem, which will then in turn imply Bernstein's theorem. This theorem is due to Osserman. So the statement starts by saying, let's let f be a global entire solution to the minimal surface equation on all of R2. Then there exists a non-singular linear transformation So I'll write this transformation as U1 is V1, and U2 is AV1 plus B V2, and we can assume that B is positive, such that V1, V2 are global isothermal coordinates on the graph. Okay, so let's just see why this implies Bernstein's theorem. So if I have a global solution of the minimal surface equation, I know that I have a global linear, non-singular linear transformation of this form, such that the new coordinates V1, V2 give me global isothermal coordinates. But we've just seen from our previous lemma that if I have these global isothermal coordinates, that's equivalent to saying that my surface actually lies in a plane. So my function must be an affine function. That's the only choice there is. Okay. Let's go ahead and prove. Let's maybe just write down the corollary first. Right. So the statement of the corollary is Bernstein's theorem. It says that if I have a global entire solution to the minimal surface equation, then that surface must be a plane. Right. So let's go ahead and prove this. Proof of Hessian's theorem. So what do I know? I know that I have a solution F solving the minimal surface equation. So this means there exist functions f and g such that the gradient of f I can write as 1 plus p. 1 plus p squared over w pq over w, and the gradient of g I can write as pq over w 1 plus q squared over w. And then I can write down the Leuven map. write down the Levy map. This way. So what do I know? I can write down my phi k's. These are going to be d uk. Okay, right. Right, so I can write down my right. I have my phi, I have my x's. Now my x's, these are defined. So this is C maps R2 to R2 is a diffeomorphism. So what does that tell me? That tells me that okay, right, so I'm sorry, I should write it this way. For each r greater than 0, I have C mapping the disk of radius r centered at the origin onto some domain. And C omega r contains the disk of radius r centered at C of 0. And now I can let r go to infinity, and we see that C actually maps all of R2 onto R2 is a diffeomorphism. Okay. But what else do we know? We know that that from the way we constructed this Levy map, we know from the way that we constructed this Levy map that the isothermal parameter that, sorry. But by construction, right, we know that these are isothermal parameters. So how do you verify that? So you can write down the dot product of dxc du1 dxc du2. That's going to be and if you compute this dot product, you'll find 0. Okay. So then what do? I can write down I can write down these functions, which we wrote down before when we investigated isothermal coordinates. And we see that these are actually holomorphic functions of the variables C1, C2. Okay, so now I write down the imaginary part. of C1, sorry, the imaginary part of C1 bar times C2. This is the imaginary part of du1 dc1 plus I du2 dc2 times du2 dc1 minus I du. This should be a 1 here. This is a 2. And I see that this imaginary part is actually minus the determinant of the following 2 by 2 matrix, dxu1, dxc1, du1, dxc2, du2, dxc1, du2, dxc2. And this determinant is negative because this Jacobian everywhere is everywhere positive. So then if I look at the imaginary part of phi2 over phi1, I'll see that this is, of course, 1 over the length of phi1 squared times the imaginary part of phi1 bar times phi2. And this is again going to be negative. And what do I have here? I have here a globally defined holomorphic function. But it's something that takes values in a half plane and therefore by Liouville's theorem, I see that phi2 over phi1 must be a constant. And I can rewrite this by saying that phi2 is a plus a minus ib times phi1. And if I rewrite all of this, I see that then du1 dc1 is a du1. Sorry, this is a 2. This is d. Now I can let V1 and V2 be defined by these equations. And what do I see? I see that dV1 dC1 is dV2 dC2, and that dV2 dC1 is minus dV1 dC2. And these are, of course, the Cauchy-Riemann equations. And what does that tell you? It tells you that these functions now are complex analytic. And then, because I have holomorphic functions, this tells me that I have, in fact, global isothermal parameters, and these are my global isothermal parameters. And that completes the proof. So let's just do a little summary of what went into this proof. A bit of a summary. Why does this work? So this works for a couple of reasons. So first of all, we know that isothermal coordinates, the existence of isothermal coordinates is equivalent to the existence of certain holomorphic functions. The next thing we know is also that the existence of these isothermal coordinates on an entire graph is equivalent to the graph being a plane. And then the final ingredient is, of course, Liouville's theorem. Which says that any entire holomorphic function, functions cannot take values in a half plane. So we see here that the proof very much relies on two dimensions. The proof is very two-dimensional. The proof relies on the fact that I have a two-dimensional surface sitting in an ambient Euclidean space. It's not very important that the ambient space is three-dimensional, but it is very important for the proof that the surface itself is two-dimensional. So this brings up the question for which dimensions n is it true? I'll say it does Bernstein's theorem hold? And the way to ask this question is to say that, i.e., if f maps Rn to R is a global solution to the minimal surface equation, which you can still phrase as the divergence of gradient f 1 plus gradient f squared equals 0, must f be an affine function. And so it's a theorem, in fact. This is true if n is less than or equal to 6, false if n greater than or equal to 7. And there are examples. So the examples you may have seen is the so-called Simon's cone in R8. So you can look at the proof for higher dimensions. You have to use, of course, a different proof, but there are other proofs that carry over to higher dimensions. The showing that this Simon's cone is actually a minimal global area minimizing graph is a little bit difficult. It requires the use of some machinery called calibrations. So anyways, that completes this presentation, and I hope you learned something there. Good, great, thanks.